In this video, we'll take a look at, in detail, the answers to this test review on curve sketching. And in the first part, there's just 3 multiple choice. We'll take a look at those first. The first question says, an interval on a graph where the second derivative is negative is referred to as. And so if the second derivative is negative, I've drawn a curve here, and I want to draw a few tangent lines. And so I'm going to draw a few of them. And 5 is enough. So the idea is this: if the second derivative is negative, that means that the first derivative is getting smaller. And so if you go from left to right here, this tangent line has a positive slope, positive value. It's fairly steep. This one's still positive, but it's not as steep. This has a tangent line slope of 0 because it's at a local maximum point. And then the first derivative, or the slope of the tangent line, turns to be negative, and then even a larger negative. So what's happening to the first derivative is going from positive through 0 to negative. So the first derivative is decreasing, and that's what it means that the second derivative is negative. And so that's said to be a concave down place in the graph because all the tangent lines are above, or the first derivative is negative. For question 2, if the first derivative is positive on a certain interval of a graph, then the function is said to be, and the correct answer is, increasing. And so if I draw a curve like this, if we were to draw a couple of tangent lines there, then notice the tangent lines are all below the curve, and they're all positive. In fact, as we go from left to right, the tangent lines are becoming steeper, and that's because the graph is curving up. And so the graph is said to be an increasing graph because the tangent lines are getting larger in slope. So that's why the answer for number 2 is A. First derivative is positive, it's an increasing part of the graph. For number 3, if the first derivative is 0 where x equals a, and the first derivative changes sign from positive to negative as we go from left to right, then there exists, and the correct answer is a local maximum. We'll go back to the first diagram here. So the first derivative, so this is the place where x is equal to a. So the first derivative is 0, and it's changed from positive slope on this side to negative slope on this side, so that's why we call that a local maximum. So that's why the correct answer for number 3 would be a local maximum. In part 2 here, we're asked to use the derivative to find the critical points and then the intervals of increase and decrease for this function. So the first thing we need to do is find the derivative. So here's our function. So we use power rule for all the different parts of this. So the 3 comes down and be negative 3x squared. Remember, you subtract 1 from the exponent to make that 2. 2 comes down and multiplies by negative 3 to make it negative 6. Decrease the exponent by 2 to 1. And 24x's derivative would be 24. There's actually an exponent of 1 here. If it's 1, we don't normally write the 1. And so the 1 comes down and multiplies by 24, so that's why it's 24. And then you subtract 1 from the 1. So that would actually be an x to the power of 0, but we don't normally write in x to the power of 0 because x to the power of 0 is 1. So that's why it's not normal to write that there. And the 7 is a constant, so its derivative is 0. So that's the whole first derivative. Now to find the critical points, we set the derivative to 0. So here's me setting the derivative to 0. And I'm noticing that there's a common factor of negative 3 that we can divide out. So that's what I'm doing here. So if I divide negative 3 into all this, I get x squared plus 2x minus 8, and of course equals 0, because 0 divided by negative 3 is still 0. And so this factors the numbers, 2 numbers that add to 2 and multiply negative 8 would be 4 and negative 2. So it factors in x plus 4 and x minus 2. So if we set each of these factors to 0, we get negative 4 from this one and 2 from this one. So those are most likely our critical points. Okay, there is a way we can check that. If the graph changes from decreasing to increasing or vice versa, they actually are critical points. And so I'm going to find the function values or y values for these. So I go back to the original function. I'm going to put the negative 4 in place of x. So there's the negative 4 cubed from the negative x cubed. Negative 4 in there, so we get minus 3 times negative 4 squared plus 24 times negative 4 plus 7 works out to negative 73. And I'll do the 2 as well. So if we put 2 in there, we get 35. So this would be the point negative 4 comma negative 73 and 2 comma 35. So to check whether where the function is increasing or decreasing, and then to ensure that these are critical points, we put the negative 4 and the 2 on a number line. And so we check the value of the derivative below negative 4, between negative 4 and 2, and then above 2. So a number below negative 4 is, for example, negative 5. Negative 5, negative 6, negative 10, anything down there below negative 4 you could use. And so we put negative 5 in the derivative. So again, this is the derivative. Don't use any simplified version of the derivative. That's not actually a simplified version of the derivative. I've divided the negative 3 out, so it's not actually the derivative. Make sure you use the real first derivative here. So we put negative 5 in place of x, and it works out to negative 21. Now the 21 part doesn't matter. The fact that it's below 0 or negative is what matters. So that shows you that on that interval below negative 4, the value of the derivative is negative, and so it's a decreasing function. So decreasing below negative 4. Then I'll pick a number between negative 4 and 2, and I use 0. 0 is a really easy number to substitute in. So putting 0 in the derivative, we get 24. So it's positive, so the graph has changed from decreasing to increasing, so that actually is going to be a critical point. In fact, it would actually mean that that's a local minimum. We weren't asked that here, but if it changes from decreasing to increasing, then the graph has to be going like this, and so it would have to be a local minimum there at negative 4. And then we'll check to the right or above 2. I use 3 in the derivative, and I got negative 21, so it's back to a negative again, and so it's decreasing again. So to answer the question here, the critical points are at negative 4, negative 73 from over here, and 235. The function is decreasing on this interval where x is below negative 4, less than negative 4, and greater than 2, and it's decreasing on those two intervals and increasing between negative 4 and positive 2. Okay, flipping over to question number 2 here. Find the local minimum and maximum points for this function and state which are local maxima or minima. And so we have the function here, so we need to take the derivative. So the derivative of 3x to the fourth would be 12x cubed. 4 comes down and multiplies by 3 to make 12. Decrease the exponent to 3. 3 times 8 is 24. Decrease the exponent to 2. 2 times negative 90 is negative 180. Decrease the exponent to 1. 8 is a constant, so its derivative is 0. So that's our first derivative. So we set it equal to 0 to find out where the critical points could be. And so notice that there is a common factor of 12x in all this. We factor a 12x out, and then we can factor this trinomial. What adds to 2 multiplies negative 15 would be 5 and negative 3, so it factors into x plus 5 times x minus 3. Don't forget about the 12x factor. So we set each of these to 0. If we set 12x to 0, we get 0 for a solution. We set x plus 5 to 0, we get negative 5. And x minus 3 set equal to 0, we get positive 3. So there's 3 places where there are potentially local minima or maxima or critical points. And so I'm going to use the, well actually I'll find the function values for them first. So I'm substituting the 3 of these back into the original function just to find the y values, because it says points, not just the x coordinate, so we need the whole ordered pair. And so if I put negative 5 in place of x, 3 times negative 5 to the fourth, which is this, plus 8 times negative 5 cubed, which is here, minus 90 times negative 5 squared plus the 8 is negative 1367. I'm just showing the calculation here from my graphing calculator. F of 0, I didn't bother showing the graphing calculator. That's a pretty simple one to do, because when you put 0 in here and here and here, this is all 0. And so you just get 8. And then we put 3 in, and this is what the calculation looks like. You get negative 343. So I'm going to use the second derivative to determine which are local minimum or maximum just by looking at the concavity. And so here's my first derivative. So to find the second derivative, we differentiate the first derivative. So 3 times 12 is 36 and x squared. 2 times 24 is 48. Decrease the exponent by 1 to 1. And the derivative of negative 180x is negative 180. And so I'm just checking whether the second derivative is positive or negative. And so I'll take the negative 5 and put it in place of x here and here. And that works out to 480. And actually, I'm showing all the calculations over here. So the fact that it is greater than 0 is what's important here. I showed that here. I'm not sure why I didn't in this calculation, but it's greater than 0. And so the graph is concave up. So if the graph is concave up like this, then at negative 5 we have a local minimum if the graph's concave up. If we put 0 in the second derivative, we get negative 180. So it's less than 0, so the graph is concave down. So at 0 we have a local maximum point. At 3, if we put 3 in the second derivative, and there's the calculation here, we get 288, which is greater than 0, and so it's concave up. So we have a local minimum again there. So negative 5, and this was the y value, negative 1367, and 3, negative 43, are the local minimum points, and 0, 8 is the local maximum point. So there's two local minimums and a local maximum. For question number 3, you're asked to find the points of inflection for this function and determine where the graph is concave up and concave down. So we take the original function, f of x here, and find its first derivative. So derivative x to the fourth would be 4x cubed. Derivative of this would be 6. 2 times 3 is 6x squared. 2 times negative 120 is negative 240. Decrease the exponent by 1 to 1. And derivative of 40x is 40. The negative 3 is a constant, so its derivative is 0. So that's the first derivative. Now we need the second derivative. So 3 times 4 is 12, and then x squared. 2 times 6 is 12, and then decrease the exponent by 1 to 1. And derivative of negative 240x is negative 240. So that's the second derivative. So to find out where points of inflections might be, the definition of a point of inflection is the second derivative is 0, and it also changes sign. So we find out where it's 0 first. So we set that equal to 0, and I'm noticing that there's a common factor of 12 here. So I divide a 12 out, and I get x squared plus x minus 20 equals 0. So what adds to positive 1 and multiplies negative 20 would be 5 and negative 4. So x minus 5 and x plus 5 and x minus 4 are the two factors. So if we set x plus 5 to 0, we get negative 5, and x minus 4 to 0, we get positive 4. So at negative 5 and 4, those are two places where there may be inflection points. We have to actually check to make sure the sign of the second derivative changes there. So that's why the number line's here. So here's my number line, and I put negative 5 and 4 on it. And so I'll check the second derivative at a number below negative 5. I use negative 6. And so I'm substituting the negative 6 into the second derivative. So 12 times negative 6 squared plus 12 times negative 6 minus 240. This is actually my calculation on my graphing calculator here. And I get 120. Okay, so it's positive. So that means on this interval, the graph is concave up if it's positive second derivative. Check a 0. I'm checking 0 here, 0 being a number between negative 5 and positive 4. So if I put 0 in place of x in the second derivative, I get negative 240. So it's a negative second derivative here, and so the graph is concave down. It must be shaped like this. And then a number to the right of 4, I went back to, well, I'll use 6 here. 6 is bigger than 4. So there's my 6 in. I get 264 greater than 0, so the graph has changed to be concave up. So it's changing concavity at each of these points, so the negative 5 and 4 are going to give us both inflection points. Now it does say points, so we should substitute the negative 5 and the 4 in place of x in the original function to find the y coordinates or function values that go with those. And so that's what this calculation is here. And so here's my negative 5 in place of x in the original function. I get negative 2828, which is, I've shown the calculation here. And then I'll do the same with 4. I get negative 1379. And so just to state our answers here, this would be the point negative 5, comma, negative 2828, and 4, comma, negative 1379. So those are the two inflection points. And the graph is concave up below negative 5, so on x is less than negative 5, and greater than 4. And then it's concave down between negative 5 and 4. And so that's the answer for question number. In question number 4, we're asked to sketch the graph of this function using a lot of the curve sketching tools like local maximum minimums, intercepts, asymptotes, concavity, second derivative test. Now this is actually a polynomial function, so there will not be any asymptotes here. So let's take a look at the intercepts first. The intercepts are one of the shorter things to do here. And so I can find the y-intercept by putting 0 in place of x. So if I put 0 here, 0 here, and 0 here, that whole part there is actually going to be 0, so f of 0 is just 4. And so that's the y-intercept. So that's why the graph goes through the y-axis here at 4. Now, to find the x-intercepts, I set the function equal to 0. And so I need to factor it. So here's my synthetic division over here to factor it. You can try factors of 4. So plus or minus 1, plus or minus 2, plus or minus 4. There's actually 6 different numbers that possibly could work. So 4 actually works. I'm showing the one it does here. You might need a little trial and error to get to the right one, but there aren't that many numbers to check. So 1, negative 5, 3, 4 is the numbers across the top of the synthetic division, and I'm using 4 here. So bring the 1 down. 4 times 1 is 4. Negative 5 and 4 add to negative 1. Negative 1 times 4 is negative 4, so put negative 4 here underneath the 3, and add those, you get negative 1 again. And negative 1 times 4 is negative 4, add to the 4 above it, you get a remainder of 0. So that means that x minus 4 is a factor. And then the other factor would be x squared minus 1x minus 1. So that's what I have written here. So I factor this into this binomial and this trinomial. Now I can't factor this, so I'm going to use the quadratic formula. So here's my quadratic formula. A is 1, B is negative 1, C is negative 1. And so substituting all those numbers in, I get 1 plus or minus the root of 5 over 2. Now I need to change it to decimals because I want to graph it. Pretty hard to know where 1 plus or minus the root of 5 over 2 is if you don't change it to a decimal. So if you add 1 plus root 5 divided by 2, 1 minus root 5 over 2, you get these two numbers. The 4 actually comes from the x minus 4 factor. So there's actually 4, well, 1 root here and then 2 roots in this, so there's 3 roots altogether. So the graph goes through the x-axis at 4, at 1.6, and but negative 0.6 right there. So that's where those 3 points come from. So next, let's take a look at where any local minimums or maximum points might be. So here's our function. So we're going to set the derivative to 0. So the derivative of this would be 3x squared minus 10x plus 3. And so we set 3x squared minus 10x plus 3 to 0, and we factor. Now the purpose of this test review is not to show how to do a bunch of factoring, so that's why I didn't show this factoring. But this trinomial would factor into 3x minus 1 and x minus 3. You could also use the quadratic formula, and it will give you 3 and a third as well. So from this factor you get the 1/3. From this factor you get, when you set it equal to 0, you get positive 3. So at 3 and also at 1/3, there is a local minimum or local maximum points. And you can guarantee which is which by checking with the second derivative. So now I'm going to go into my second derivative here. So there's the first derivative. So the derivative of 3x squared would be 6x. Derivative of negative 10x is negative 10. So we set that equal to 0. Bring the 10 over, divide it to 6. You get 10/6, which is 5/3. So that's a potential inflection point. Now what I'm going to do is check the, now actually notice that the 5/3 is in between the 1/3 and the 3. So my potential point of inflection is in between what are probably a local minimum or local maximum. If you're looking over here, you're kind of looking ahead, kind of cheating a little bit because we don't actually know what the graph looks like yet, but we're getting there. So what I'm going to do is I'm going to find second derivative at 3 and also 1/3. And that'll tell me what the concavity is, so which is a max or min. And if concavity changes, then this actually is a point of inflection. Okay, so I kind of get a couple things out of the second derivative here. So if we put 3, actually I'm going to do the second derivative down here. I forgot this is actually just my function values. I want to find the y values that go with each of these. So if I put 3 in the original function, so original function here, I get negative 5. So that'll be the point 3 comma negative 5. If I put the 1/3 in, and actually I showed the whole calculation here, I get 121 over 27. For the purpose of graphing, of course, it'd be nice to know exactly what that is. So that's why I'm bringing this over. If we divide 121 by 27, it's just under 4.5. So just so we know where to graph it. So that's the point 1/3 comma 121 over 27. So it's 1/3 comma almost exactly 4.5. So here's my second derivative. So I'm going to check the second derivative again at the two places where I think I have local maximum in, at the 1/3 point and the 3 point. So if I put a third in, and again, here's my second derivative, 6 times a third minus 10. 6 times a third would be 2. And so 2 minus 10 is -8. So it's less than 0. And so the graph is concave down at a third, the 1/3 comma about 4.5 point. And so there's a local maximum at that point. So let's do the 3. Put 3 in place of x. So 6 times 3 would be 18. Minus 10 would be positive 8 in that case. So it's a greater than 0, positive, second derivative there. So the graph has to be shaped like this. So there's a local minimum at 3 comma -5. Now, just so we can say what the actual point of inflection is, let's take the 5/3 and just like we did here, also put the 5/3 back into the original function, and we get -7 over 27. You can go through all the calculations if you wish. So the point of inflection is 5/3 comma -7 over 27. We found that the graph was concave down less than 5/3, which is where we checked this, and concave up on greater than 5/3 when we checked the 3. Remember, it was positive. So because concavity changed, x equals 5/3 is an inflection point. So if we graph all those points, here's the 1/3 comma about 4.5 local maximum, and then this is the 3 -5 local minimum. If we were actually to plot the point of inflection, that's about 1.7. And actually, if we bring the calculator over here, if you divide 7 by 27, I didn't bother with the negative in, we would know it's negative. It's about almost a quarter. So the point of inflection would actually be approximately just down around here somewhere, just below that x-intercept. And so the graph is concave down here, so that's why we know it goes like this. And this is the local minimum, so it's concave here and passes through the x-axis there. So that's how we get the shape of the graph. I've actually put a graphing calculator sketch on here as well, and of course it has the same general shape as the one above. In question number 5, we're asked to find the horizontal and vertical asymptotes for this rational function. So let's take a look at the vertical asymptotes first. The vertical asymptotes are values for x that make the denominator 0 and hence the function undefined. So we can find the vertical asymptotes by setting the denominator equal to 0. And we can factor this trinomial. We'll look for two numbers that add to -3 and multiply to -10, and -5 and 2 are those numbers. So this would factor into -x minus 5 and x plus 2. And so if we set x minus 5 equal to 0, we get x equals 5 for one of the vertical asymptotes. And if we set x plus 2 equal to 0, we get x equals -2 for the other one. So those are the two values that make the denominator 0 and hence the function undefined. So those are the two vertical asymptotes. To find the horizontal asymptotes, we take the limit of this function as x tends towards infinity. And notice that the highest power of x is in the denominator. There's an x squared here, whereas there's only a 3x to the first in the numerator. And whenever the higher power is in the denominator, this limit will always be 0, and that's why the horizontal asymptote is y equals 0. Now, you can numerically get an idea what this asymptote is as well if you take and substitute a large value of x or number in for x. So for example, let's say I put 1,000 in place of x, a relatively large number. I could put something bigger. So 3x minus 4, so that's the 3 times 1,000 minus 4. And then divided by, and in the denominator it's 1,000 squared minus 3 times 1,000. And then minus 10. And we'll close the bracket. And so notice that is quite close to 0. The larger number you took and put in place of x, the closer it would be to 0. Now, one thing I want to point out is that this -4 and the -3x minus 10 at the bottom, they're lower terms, and so less important or less influential terms, if you actually just did 3 times the 1,000 on top, divided by, and just put 1,000 squared in the bottom, notice how close that is to this calculation here. So the -4, the -3x, -10, they're actually quite insignificant as x becomes large. The most important term is the highest power on the top and the highest power on the bottom. And if you actually find the ratio of them, then that will give you what your limit is. So on to question 6 here now. So we're given a velocity time graph, and you have to scroll down a bit. So this is the velocity time graph. It's made up of 3 line segments. And we're asked to find the displacement function from that and then draw it. So, and we're told that we're to assume that the constant is 0 for the first displacement function, so it starts at 0, 0. And each subsequent one starts where the other one left off. That's what it says near the end here. So the first segment that I'm referring to here is this line segment along here. And in 3 seconds, so from 0 to 3 seconds, it displaces from 0 to 24. And so the rise would be 24, and the run is 3, so I'm just doing slope rise over run. And so 24 divided by 3 is 8. So the equation of this line, and notice it goes through the origin, so the y-intercept is 0, or v-intercept is 0, would just be v equals 8t. So in order to find the displacement function that has this as a velocity function, we find, and this is actually called an antiderivative. We're actually going in the opposite direction of differentiation, because if we differentiate this, we should get the velocity function. But we know the derivative first, the 8v equals 8t, and we're trying to find the original function. So we do the opposite of the power rule. Right now there's an exponent of 1 here, so the opposite would be adding 1 to that. Remember, for the power rule you normally bring that constant down and subtract 1 from the exponent. So we add 1 to that, so the t becomes squared, and divide by that too. And so I'll call C1 the first constant for this. We are told that the displacement at time 0 is 0, and so that would mean that C1 is 0. If you want to see what that looks algebraically, I'll show it to you here. 8t squared divided by 2 simplifies to 4t squared. So if we call this plus that constant C1 in the end, well, if we put 0 in place of the displacement, and this 0 in place of the time, it actually looks like this. And so this is 0, and so that's why we would get C1 to equal 0. And so let's just get rid of that writing there. So d equals 4t squared. Now, in order to graph this, we can make a small table of values here. And so notice the times go from 0 to 1 to 2 to 3 seconds. That's the times for this interval. So if we take our graphing calculator here, and 4 times, I'll start at 0 because 0 is the first time. So 4 times 0 squared, of course, is 0. So that's why it starts right here. If we do 4 times 1 squared, that's 4. So at 1, we should be at 4, and we are. And then we'll put 2 in place of time. And so at 2 seconds, we're at 16, which is right there. And to finish this part off, if we put a time of 3 in, 36, so that's why it goes up to 36 right there. So I've plotted actually several points to draw that parabola. So that's the first part. So second part, second segment is this horizontal segment which goes from 3 seconds to 5 seconds. And so notice the velocity is constant at 24. And so the slope is 0, so the equation would be, and I'm just using y equals mx plus b, except it's v and not y up here, and it's time t instead of x here. So y equals mx plus b would equate to v equals 0, because the slope is 0, v equals 0t plus 24, or just v equals 24. So to find the displacement function, it's 24t that you differentiate to get 24. So d would be equal to 24t plus, I'll call it constant 2. Now, the way we find that constant is this second part of the graph must start where the last part ended off. So remember, at 3 seconds here, we had a displacement of 36 meters. And so d of 3 would equal 36. So if we put 36 here and 3 in place of time, we get 36 equals 24 times 3 plus that constant. So 24 times 3 is 72. So if we take that 72 over and subtract it from the 36, we get negative 36 for the constant. So the displacement function would be equal to 24t minus 36. And so that's what we're supposed to draw next. That's what this line is here. And so notice it goes from a time of, well, it starts at 3 and ends at 5 seconds. So if we plug, just to check here, 3 in place of time, we get 36. So you see at 3 seconds it's at 36. That's the beginning. So I'm going to do 4 and 5 seconds as well. It's a straight line, so we don't need a ton of points to graph it. So there's 4, and let's do 5 as well. So at 4 seconds it's at 60, at 5 it's at 84. So remember, 460 and 584. So 4, it's at 60, and at 5, if you want to plot a point, it's at 84. And so we can just join those points together, and that's that straight line in the middle. So last part, the third segment, is this one right here. And so from 5 seconds to 7 seconds, so 2 more seconds again, it's going from 24 down to 0, so the rise would be negative 24. It's gone down 24 in a time of 2 seconds. So the slope of that's negative 12. So again, using y equals mx plus b, it would be v equals negative 12t plus b, and I need to find b. Well, b would be, you can tell that b is something up here, probably in like the 70-80 range, something like that. And so we could substitute a point in from here. So the 524 point is a point in that. I could use other points, but that's the one I'm going to use. So we'll put 24 in place of v and the 5 seconds in place of time. And so 24 equals negative 12 times 5 plus b. And so that's negative 60. When we bring it over, we would be adding 60 to 24. So that's why b works out to 84. So the velocity function would be v equals negative 12t plus 84. Well, now I need to find the displacements. I need to find the antiderivative of this, or what do you differentiate to give you negative 12t plus 84. So we do that opposite of the power rule thing. So we add 1 to the exponent and then divide, which is 2, and then divide by the 2. The derivative of 84t is 84, so this has to be 84t here. Plus I'll call it constant c3. Now this simplifies to negative 6t squared plus 84t plus c3. So now I'm going to sub in 584 because this next displacement function must start where the last one ended off. Remember, at 5 seconds we had a displacement of 84. And that was actually that calculation right there. And so 84 goes in here and 5 goes in here. And so 5 squared is 25 times negative 6 is negative 150. 84 times 5 is 420. So when we bring this over, we'll be adding 150 and then subtracting 420, so the constant becomes negative 186. So substituting negative 186 in here, we get d equals negative 6t squared plus 84t minus 186. And so to graph this now, bring the graphing calculator back one more time. So this part goes from 5 to 6 to 7 seconds, so it starts at 5 seconds. So let's substitute 5 just to check that one. Plus 84 times 5. Of course, it should give us that 84, I believe it is. And it does. So that's the beginning, so that it does start in the right spot. So let's substitute 6 and then 7 in. So time at 6 is kind of in the middle of that. Gives us 102, and then we'll do 7 as well, because that's the end. 7 seconds. So remember, at 6 it's 102. As soon as I start moving the graph, this calculator disappears. At 7 seconds it's 108. So 6 is 102, 7 is 108. So let's get rid of this. So at 6, which is straight up from here, So right there, it's at 102. And then 1 second later, which would be here, it's at 108. And so of course, it starts where the other one left off, and we can draw it through those few points. This is a negative quadratic function, as you should expect from that equation. And so that's what the whole displacement function looks like. And that's the end of the video.